Alright, we're going to start a new unit in chemistry, Unit 7. I know it says Unit 6, but it's really supposed to be Unit 7. And the unit is going to cover the topic periodicity. Periodicity deals with trends in the periodic table. These trends are repeated patterns, and so they are trends that occur over and over again as you look at the periodic table. And so I would recommend that you have a periodic table out with you as you go through these lectures as we look at the trends within the periodic table. Alright, Lecture 1 deals with a very important topic called effective nuclear charge. We'll explain what effective nuclear charge is, but let me tell you that effective nuclear charge is going to be the central idea about why trends occur within the periodic table. So it's important that you understand Lecture 1 before you go on to any of the other lectures. The essential questions that will be addressed in this lecture is: what is the effective nuclear charge? What is the periodic trend for effective nuclear charge? Those two questions need to be answered before you move on to any other lecture. And these questions will be addressed on the quiz for this lecture in class. Okay, so first of all, what exactly is nuclear charge? I wrote down some important points here that you should copy into your notes about nuclear charge. So let's look at these individually. Nuclear charge, by definition, is considered the nuclear attraction for valence electrons. So basically, it just measures how much or how attractive the nucleus is to the outer or valence electrons. The more protons that's in the nucleus, the greater the attraction for valence electrons. And that should make sense to you, because if you remember that if you have a proton, it has an attraction for an electron. Let's lay out here in this valence shell. And if you add more protons, then there's going to be an even more or a greater attraction on that electron in the valence shell. Alright? Now, it doesn't matter how many electrons. If you look at this diagram over here, it doesn't matter how many valence electrons are in the outer shell. Each valence electron is attracted to the nucleus with the same attractive force. So we have a nucleus here that's going to attract this electron here with the same attractive force as this electron here, due to the fact that both of those valence electrons are at equal distances from the nucleus. Alright? So keep that in mind as we go through this. Now, the nuclear charge increases with increasing atomic number. Alright? So keep that in mind. And then the last important thing is that when the valence electrons get further away from the nucleus, then the nuclear charge is going to get smaller. It's going to actually decrease. So we can kind of look at this idea. Here's a proton, here's an electron. There's an attraction between the electron and proton. If you have another proton and the electron is further away, then if you look at this closely, the attraction gets smaller here as the distance gets further away. Alright, now, so there's two ideas on nuclear charge that you have to think of. The more protons there are in the nucleus, the greater the attraction for the valence electrons, and the closer the electron is to the nucleus, the greater the attraction of those electrons. Those are two important points that you have to think about with nuclear charge. Alright, let's go on and talk about this idea of shielding. Now, if there are electrons that are considered inner electrons, they are going to shield or act as a shield for the valence electrons. So if you look at our diagram over here, the nucleus, of course, is right here, and then we have some inner electrons right here, and we can say that this is the, I don't know what shell this would be. Let's say it's the second shell, and first shell is not showing, and let's say that this is the third shell. We have two outer electrons here, and these three inner electrons that are in X's here are going to shield the outer electrons from the nucleus. And so because of that shielding, we call this the shielding effect that occurs. And this will only occur if there are inner electrons that will shield the valence electrons. So the consequence of this, why is this important? Actually, we'll come back to this. So why is the shielding effect important? How does that affect the nuclear charge? Well, I wrote down 3 points here that you should put in your notes that are important. So first of all, the shielding effect reduces the nuclear charge then, because the nucleus, because those inner electrons kind of act as a shield, the nucleus cannot reach out as strongly to those valence electrons and attract those electrons. And so the shielding effect does have a pretty important factor on the attraction between the nucleus and the valence electrons. And then the last point is, the greater the shielding effect, then less attraction to the nucleus has on the valence electrons, which we kind of pointed out. So going back to this diagram here, again we can see the shielding effect with our valence electrons here and here, and then our inner or core electrons, and the nucleus here. The nucleus just cannot reach out with a great attractive force because of those inner electrons acting as a shield or a force field, blocking the nucleus from the outer electrons. Right? Alright, so now let's talk about repulsion, because there's also some repulsion forces that will affect the nuclear charge. So the inner electrons not only shield, but they also repel the valence electrons. Repel the valence electrons, and then therefore they're gonna push the valence electrons further from the nucleus. And remember, when the electrons get further, when those valence electrons are further from the nucleus cannot attract those electrons as easily as if they were closer to the nucleus. So we're going to see a reduction in nuclear charge on the valence electrons. So if we can come back to our diagram here, you can see the repulsion forces. You can see the repulsion forces here. Repulsion due to these inner electrons, and that's going to push those valence electrons further out from the nucleus, reducing the nuclear charge. Alright. Oops, go back. So, what does this all mean? What is repelling and shielding going to, how is that going to affect the nuclear charge overall? Okay, and so here are some important points that you need to write down. The shielding and repulsion together create a new terminology called an effective nuclear charge. And essentially what that means is that the effective experience by the outer electrons is going to be reduced so that it doesn't have a full attractive charge. So what I'm trying to say is that because of shielding, because of repelling, the nucleus cannot attract the valence electrons with a full charge. Just cannot do so. And maybe that's what you really should write down is the full charge right here, the full charge. With the shielding, with the repulsion, the valence electrons cannot receive a full attractive charge from the nucleus. So therefore, the real charge that the valence electrons experience from the nucleus due to repulsion, due to shielding, is referred to as the effective nuclear charge. That's what really is the charge. That is the real charge that the electrons, valence electrons, experience. Alright, so let's look at this a little bit further in detail here. With these 2 points, the effective nuclear charge experienced by an atom's outer electrons increases with the group number of the element. Alright, so that means that as we go across the periodic table left to right, the effective nuclear charge does increase. And here's an important trend. It increases across the period, but approximately remains the same going down in a group. Alright? So if we look at this a little bit closer, is what is the periodic trend of effective nuclear charge? Okay, so first of all, I want you to look at this periodic table. Ignore the ionization energy there, and ionization, just ignore what that says, right? And so what we want to say is simply, as we go across the periodic table left to right, the effective nuclear charge charge increases. Okay, it's going to increase as we go left to right, and we'll talk about why that does in a little bit. Alright, as far as going down the periodic table, the effective nuclear charge remains approximately the same, and we'll talk about why that is too. Alright, so make sure you kind of understand that idea. Again, one more time, the effective nuclear charge increases as you go left to right across a period, but remains approximately the same as you go down a group. Alright, so why is this the case? Why is this occurring? Well, the increase in effective nuclear charge across a period is due to an increase in the number of protons. So we're increasing the number of protons, and so since there's more protons in the nucleus, it's going to have a greater attraction to the valence electrons. Now what about shielding? Well, the shielding effect does not increase as you move across the periodic table. And since the shielding effect has no bearance upon the nuclear charge as you move across the periodic table, as we increase the number of protons, then the effective nuclear charge is also going to increase, or the nuclear charge. Now this is not true for the transition elements. Okay, with transition elements, we actually see the shielding effect taking an effect here, and the shielding effect is going to offset the increased number of protons. So essentially the effective nuclear charge doesn't really change much when we're talking about transition elements. Alright, so you might want to write that in your notes, that the shielding effect it increases with the transition elements, and so it offsets the increasing number of protons, and therefore there's not a lot of change in the effective nuclear charge going across the periodic table when you hit the transition elements. Alright, now what about going down? Again, when you go down a group, the nuclear charge remains approximately the same. Why is this? Because the increased number of protons is offset by the shielding effect. So the shielding effect increases as you go down the periodic table, because you're adding more inner electrons as you go down the periodic table. And as you add more inner electrons, the shielding effect increases. So even though you're adding more protons as you go down the periodic table, if you look at your periodic table, you'll see that going down a family, you increase the number of protons, but the shielding effect is also increasing. So those two are going to offset each other, and therefore the nuclear charge remains approximately the same. We can look at this by looking back at our periodic table here. So we can look that as we go down, use this. As we go down the periodic table, the shielding effect increases, but also as you go down, the number of protons increase. Because the protons increase and the shielding effect increase, they cancel out each other, and therefore the effective nuclear charge remains about the same. But as you move across the periodic table, the number of protons increase, but the shielding effect remains approximately the same. So therefore the shielding effect has no bearance on the effective nuclear charge, really, and so the effective nuclear charge is going to increase with the increasing number of protons across the periodic table. Right, so that is essentially all for this particular lecture. So make sure you take really good notes. What's really important is to understand what the effective nuclear charge is and the trends of the effective nuclear charge in the periodic table, why they are that way. Alright, so that is all for this lecture.